morning, everybody. Welcome to another Pretty Agile meetup. We're really excited today to invite and have another SAFE fellow join us today, Harry Koehnemann from Scaled Agile. Harry's been in the world of embedded systems development for a really long time, and we've known Harry for a long time. He's been a great supporter of Pretty Agile. And I'm an aerospace engineer, so I'm excited whenever I get to hear Harry talk about this really important topic of hardware engineering and meets Lean Agile development. Harry, thanks so much for joining us. Really excited to have you here. Why don't you
My pleasure. Go ahead.
Yeah, go ahead.
Okay, great. Yeah, thanks for having me. One of the topics that's near and dear to my heart is how hardware engineering and system engineering and big system building addresses Lean Agile practices and Lean Agile development. That's something that, as Adrian mentioned, I've been doing for quite some time in my career. I got involved about 20 years ago with aerospace and defense companies, and I've kind of spent quite a bit of time taking practices I grew as a software engineer by nature and kind of by heart, but bringing those best practices into organizations. And I'm excited now this year. I think we've seen a big pull from hardware. Before, it's been kind of us in the software community going into hardware saying, you know, you're not delivering fast enough. We view you as a bottleneck. And in the past, I think it's the hardware folks that are coming to us and say, we want to go faster. So this year, and I don't know why, but there's disruption. Certainly a lot of industries like automotive and other places, I think that's trying to push faster development of products. So the presentation we have here today is going to talk about several agile practices and how they apply to hardware, but also a little bit of conversation about tipping, right? How do you go to hardware engineers and explain why would you do agile, and what does agile even apply to hardware? A lot of times you hear the conversation that, well, agile is what software people do. We have our own method and our own processes and practices that we're supposed to use. And trying to explain to them, well, agile really is not about software, it's more about just product development. We'll discuss that when we get there. So, oops. Great. So here's our agenda for today. Want to start with why, which is, you know, why do we want to use Agile? Why do we want to do Lean and Agile? And we'll go back to SAFE's roots and talk about that just for a few slides, and then explain that Agile really is about product development. It's not really about software development. And then we're just going to pick on three of the practices: building the system, or specifying system incrementally, designing for change, and then frequently integrating that end-to-end solution. So practices that, you know, if you're a software person, this makes sense, and it's something we've been doing for the last couple of decades. But for hardware engineers, it appears to be more of a challenge. So what are practices? What are ways we can explain how they can do these things in their context? So let's start off with talking about the value of continuous learning. If you're a SAFE person, you've probably seen this slide before. It's how we've been explaining why SAFE, or why business agility. Why do business agility? And the notion is that we're in the middle of an industrial economic revolution around the digital age, right? And this is research by Carlota Perez, where she looked at various economic disruption events that occurred. The latest one is the digital disruption, you know, and looking at, okay, there was a massive amount of capital influx. For example, in the Roaring 20s, there were 300 automotive companies in Detroit alone, right, at the age of oil and mass production. Then there's this turning point where there's consolidation and the victors emerge. And one could argue that we've gone through some of the victors in the digital age. I don't think that digital retail is going to disrupt, anybody's going to disrupt Amazon and digital retail anytime soon, as an example, right? They kind of own that. However, I don't think it's been one everywhere. And certainly in the cyber physical space, I don't think the victors in automotive and the victors in medical device and the victors in a lot of these other spaces have been decided yet. So I think we're still in the deployment period in various industries in the digital age. And that's really a unique opportunity for the folks that are in hardware. I borrowed this slide. Actually, we borrowed this slide, I should say. I worked with Jeff Shupak and some others on presentations like this. But Mick Kirsten and Gene Kim gave a talk at the last DevOps Summit, where they looked at Carlota Perez's research. By the way, a lot of us found Carlota Perez's research from Mick Kirsten's book, Project to Product. And in there, they've advanced that. Well, they haven't advanced, but they've added some thinking, which is there was a unique management method with every one of those revolutions. Taylorism, Fordism, and subcontracting, right? There were something introduced to how we manage the work and how we manage the people. The question that we want to posit is, what is the new management method for the digital age? for the knowledge workers and for things that have a lot of uncertainty and a lot of unknowns, that the traditional management methods don't work in that context. So we're going to posit that it's one of continuous learning. That's why you see in SAFE the continuous learning culture, right? We have to do a better job of creating an environment that encourages learning. And for hardware folks, a lot of them can resonate with examples that are hardware based. And I think a good one is the race for flight. How many people have heard of the Wright brothers before? Most people, you know, raise your hand. Right? They're credited, whether it's true or not, with being the first to flight. How many people have heard of Samuel Langley before, out of curiosity? Yeah, a handful, not as many, but a handful. Yeah, so Wright brothers are famous because they discovered flight. Samuel Langley, a lot of people haven't heard of, but they at the exact same time, right? These two incidents took about the same time, back in 1904 or 5, within months of each other. Samuel Langley was well funded by the Smithsonian Institute, as a matter of fact, to go create the first flying machine. And he designed a single point flying machine, tried to innovate on that single point flying machine forever. And it was never going to fly. In fact, it never flew because it had fundamental design flaws that wouldn't allow it to fly. If you know much about the Wright brothers, they took a different approach. They took one of experimentation and learning. They looked at what are the barriers, what are the risks, what are the unknowns. We don't know how to generate lift. So they invented the very first wind tunnel ever to go do experimentation with wing shapes. Once they found the best wing shape, they said, well, let's make a kite. Let's actually make a kite, weigh it, see how much lift we can generate off a kite, made gliders. They experimented along the way to learn about how to make lift, once we can make lift, how do we control the plane? And then once we can control it, how do we generate power within the plane? So they took an iterative approach to learning instead of taking this big bang approach up front. And this is a fundamental change for how most engineers think. Most engineers think in terms of, well, you got a problem, let's work on specifying what the requirements are going to be, designing the solution, and then just implementing it. In fact, ironically, I just had a conversation with one of our big 3 automotive manufacturers this week, and they're still, even though they're adopting Agile and they're a safe company, their hardware engineers still have that same exact mindset of, oh, well, we have this vehicle function that we have to do. Well, let's spend the first PI doing the requirements for it, and the next PI doing the design for it. Right? It's still the mental model that they have. You know, so it's what I like about this race for flight. It's a fundamental way of saying, no, you've got unknowns and uncertainty. And the only way that you can't plan your way out of uncertainty, you have to go build something and gain new knowledge to get out of uncertainty. All right, oops. With that as a backdrop, the next conversation is, well, hardware has its own method, right? The waterfall method we just described. Agile is what hardware people or what software people do. And then we want to dispel that rumor. We can quickly dispel it by talking about the new product development game article. How many people have heard of this article before, the new product development game? I love cameras on, by the way, Adrian. That's pretty cool. I can see actually people raising their hands or not raising their hands. So many Agilists have heard of this before because it is the root of Scrum, right? Scrum got its name Scrum from this article where they contrasted a relay race where we hand off the baton, right? So the goal is to try to get a baton across the finish line first. Well, how do you do that in a relay race? Well, I do my part, I hand it off to Adrian, she does her part, she hands it off to M, who does her part, right? So there's handoffs, right, that move the system through. Well, these folks were observing product development in these innovative environments. They were observing it's not a handoff of functions. Instead, it's swarming, it's rugby, right? We're on a perfect crowd to talk about rugby, right? Australia, right? Instead, it's all the people work together collaboratively to move the ball down the field together, no handoffs. And that's frankly where the term Scrum came from for the Scrum method. And in this article, this paper in the Harvard Business Review, they noticed certain characteristics about these products that were being developed. There was built-in instability. There was a lot of unknown and uncertainty. The leaders didn't come and say, here's a spec, go build it. They said, here's a problem we have. We don't know how you're going to solve it, but we give you the psychological safety and we give you the autonomy to go figure it out. The product teams were organized around product, right? They were self-organizing. They weren't a bunch of silos. They were cross-functional teams that built them. They had overlapping development phase. It wasn't requirements, then design, then implementation, then test. They called it overlapping, and what we would call it just continuous, right? It's continuous flow of value. Anyway, a lot of the characteristics that we see in Agile came from this article way back in 1986. And notice the companies they interviewed. They weren't a bunch of software companies. It was Xerox making copiers and Canon making cameras, and these weren't software companies. They were product companies. And that's really the message we want to get across, is that Agile is a product development method. It's not a software method. And really the goal of Agile is to deliver something quickly to get fast feedback. That's really at its roots. And so if we take this traditional approach to specifying and designing and then implementing and then verifying and eventually giving something to the customer, we have a long delay in how we're going to get feedback. Right. So if we look at this process, which is very typical, we'll wait months or years a lot of times to get feedback on this thing that we're building. Instead, we want to do things in smaller batches, right? Smaller chunks of work. And the main goal is that we want to build something to get feedback. Is it more expensive? Yeah, it's more expensive. Harken back to 20 years ago. Anybody around from 20 or 25 years ago doing software? Did we have these nice little Kubernetes with microservices and the ability to make a small change and deliver it through this pipeline in about 4 minutes to get feedback? We did not have that 20 years ago, right? Instead, I would write my change and I'd kick off this 4-hour build, depending on how big the system was. And then I'd have to wait to load it up on a board. It encouraged me to do bigger batches, right? It encouraged me. So I wouldn't test things every 4 minutes. I would test things maybe once or twice a day because we had bigger batches. It was the nature. But over time, in the last 2 decades, we've gotten better at software. We've recognized that we have to build out the infrastructure to take small engineering changes to be able to get quick feedback on them. Well, we have to have empathy for where the hardware folks are today. They're not at that same place. They're emerging and they're evolving. There's technologies like 3D printing and digital engineering and integrating engineering models that are going to help us get there, but they're not there today. So, but we still have this mindset of wanting to do incremental delivery. It's not going to be every day. I'm not going to manufacture a new part every iteration, every 2 weeks, probably. Maybe I'll 3D print a mock-up. Maybe I'll do some kind of prototype. Maybe I'll just do some kind of analysis in a model. But we have to get out of there thinking that they're going to be manufacturing a new part every iteration. And instead, we want them to be focused on what? Learning every iteration. What don't we know? What don't we know now that's our biggest risk? And what experiments or designs or analysis can we do in the next iteration or the next increment to mitigate that risk and gain new knowledge that we're going to make the solution by the time we get to the end. So that's really the goal, is to try to build things in small chunks to get fast feedback on those changes. Now, to make this happen, as we all know, we have to have agile teams, right? You've probably seen this slide before. They have all the skills and authority necessary to build their part of the system. Cross-functional works in hardware too. I've certainly worked at organizations. In fact, 10 years ago, we were working at organizations that had mechanical engineers and software engineers on the same team. So that's nothing new. It's a norm. It's not something that most people are comfortable with. We like working with our peeps, right? Do we always need to make cross-functional teams? Well, it kind of depends where the innovation is. In my experience, if there's something that's highly innovative, the example there was on a missile where there was a new nozzle, and the material they were going to use and the algorithmic control they were going to use, they didn't know how it was all going to work. So they put a cross-functional team together to go figure those things out. It was interesting. After about 8 or 10 months, I forget the actual time frame, but eventually, when you went to the daily stand-ups or the iteration planning events, they kind of became almost 2 teams. Once they had the innovation resolved, well, the mechanical engineers were going to do the next several months of just doing their design. We're just going to do our designs and our materials stuff, and the software people are going to write their control logic. So at that point, it almost became time to reorganize, right? The innovation had been resolved. They don't really need to be on the same team anymore. We're going to do our part, we're going to do your part, and then we'll integrate those things later, right? But certainly it does make sense to do cross-functional teams whenever there's a lot of dependencies between the work, and usually there's a lot of dependencies when something's new and innovative. As we all know, that teams can only rebuild things that require more than 7 plus or minus 2 people, more than 10 people. So we have this notion of an agile release train, right? That's a team of teams, and that has all the skills necessary and authority necessary to deliver something substantial, right? So as we scale teams, right, we need bigger systems, need a team of agile teams. And that really gets us into the conversation about development value streams. So that agile release train is a realization of development value streams that support an operational value stream. So in SAFE, we talk about, if there's some non-SAFE people, we talk about the operational value stream. It's the actual, there's a customer out here that's using our product, they're driving our car, or they're talking to our ATM, right? That's the deployment of the system that we have made and the usage of it in the operational environment. Well, back inside of our development world, somebody has to build the car, build the part of the car that the end user, the customer, is using, or build the ATM system and the software and the firmware that go in that ATM system. So I like to look at a bigger example of that, a more realistic example. This is an example of an autonomous driving scenario where there's a rider that wants to go from a source location to a destination location. So we're saying take it from here to here, and the steps along the way are we have to plan a route, we have to get the passenger there, they want to track their journey, and they may need to get assistance along the way. And there's some systems, and we sell those different systems in SAFE as those yellow things, right? There's a mobile app to plan my route and communicate whatnot, maybe OnStar to get assistance. But that vehicle system, that vehicle product, that's built by tens of thousands of people, literally across multiple supply chains, across different organizations, right? There's a whole supply chain of folks that contribute to that. And so that's a deeper conversation. A lot of times we talk about people that I don't build the yellow car. I build a piece of a piece of that car that gets integrated in another piece that eventually gets integrated into the car. They're down in the bowels of the supply chain, right? And so we have to have a conversation with them about, well, who is your customer? In fact, if anybody has done a value stream identification workshop, or has taught implementing SAFE, if there's any SPCTs out there, if you taught implementing SAFE or intended to implement SAFE with these folks, it always kind of goes off the rails because they talk about who's their customer, and they say, oh, well, let me grab my little drawing tool here. Who's my customer? Well, if I'm doing infotainment, my customer is General Motors, who's buying my infotainment. In fact, I worked on Sync Gen 3 for Panasonic Automotive. We were doing the infotainment systems for all the new Ford vehicles about 8 years ago, Sync Gen 3. So we referred to Ford as our customer. Well, if I start looking at Ford as my customer and start asking questions about, the behavior of the system, it goes off the rails to do value stream and identification. Really, there's multiple customers to these systems. Certainly, if I'm doing an infotainment system, there's a rider up here that's going to use my product, right? They're the end user that's going to actually touch the screen. This thing has to be built, this thing has to be manufactured and assembled somehow. So they're kind of a customer too that's designed for manufacturing, designed for manufacturability. Eventually, this thing has to be maintained and supported over time. So typically with these systems, especially large systems, we have many stakeholders or end users, as we would call them. In fact, if anybody has done any use case analysis, we would call them actors, right? Who has an interface to our system we have to design and build the system for? We have many of those folks. And better empathizing and understanding every one of these actors is important. And in fact, usually as a tip, if you ever do the value stream identification workshop and you're in a supply chain, you typically want to go out to the rider. That's usually the first one you want to talk about is who's actually using my system. And that will give you better results of organizing around value than if you try to organize around the systems that. It's funny because if you look at your direct customer and you look at the systems that are involved with that, you have a requirements management system, you've got some kind of a billing system because you got to bill and bill hours back and forth. It just really goes off the rails. Anyway, I digress. So we have guidance and SAFE to talk about this. Certainly we've got design thinking, right? So we can use design thinking, personas, empathy maps, journey maps, understanding the customer journey for every one of those customers. Certainly makes sense for the end user, right? What's their journey? What's their experience? What do they think? What do they see? What do they feel? Does that also apply to how this part's going to be manufactured? How do they think, see, feel? Of course it does. And then operations, as people maintain and evolve this system over time while it's in the production environment. And then certainly it also doesn't hurt to do it at this level as well. But usually we're focused on the operational value streams that our system is going to be operating in. All right. So that's the kind of explaining agile product, the why, and the explanation of agile product development from a hardware perspective, right? Just giving an overview of how hardware development fits in. It's really about product. Agile is really about product development and how at scale, especially, hardware developers fit into the context. Now, specifically, we want to talk about some of the agile practices and how hardware needs to fit into them. And the first one is really we've got to specify that system in smaller batches. Nothing gets in the way larger than big batch specifications, right? It's almost a non-starter. I can't start building anything if you can't begin with telling me what to build. In fact, if anybody's done one of those value stream mapping exercises, I've done those folks with government folks before, the value stream mapping exercise, and it ended up being 2.5 years from an idea to actually getting it released to customer accessible. And where are the bottlenecks? Right, the bottlenecks aren't in we can build it faster. We're trying to, can we build it faster? Sure, we probably could. and that's going to save us a week or two or a couple months. But it takes 9 months for the government, working with the government, to figure out what the next feature is going to be. That was a 9-month process. Or it takes a year. Once we get our feature handed to the government, it took a year to go through their validation process to actually be able to deploy it. So a lot of times when we look at where the bottlenecks are, a lot of times they're up front and even figuring out what to go build, right? And that's why it's so powerful. It's such a powerful concept for an agile team to have those practices. They define their own work, right? We need to be able to define our own, specify our own work, define, build, test, deploy, right? Those are fundamental characteristics of an agile team. And that's why define is a big bottleneck, right? Deploy is a big bottleneck, right? The two endpoints are usually the biggest bottlenecks we have. That's why empowering teams and arts with that authority is immensely valuable to accelerating flow. So we have to get them to think differently about specifications. Most will have seen or heard of the traditional V model. It's not the same as waterfall. Don't say waterfall because they'll get offended by that. It's because it isn't really waterfall. It's a variant of waterfall, I would argue. But it does encourage big batches of requirements to flow down into big batches of architecture and design, into big batches of implementation, to big batches of verification, validation. And all we're asking, say, all these activities are important. We are not going to take away any of the engineering practices, right? But instead, we're going to be doing them in smaller batches and doing them incrementally. And we explain it more in safe terms, right? You're going to be doing your analysis and design work, but we're going to store that in this fixed variable solution intent. Right in the note. Oh, I don't have this is an older slide. I apologize. And what I've added to this is, we start with the fixed variable is an important part here. We're going to start out with, at the end, we're going to have, 1,000 shall statements. The system shall do something, right? But when we start, we may have 100 of those shall statements. There's a certain set of things that are fixed, right? There's a certain set of things that are fixed here. The vehicle will have 4 riders, right? The vehicle will be gas-based, or the vehicle will be electric-based, the vehicle will be hybrid. There's things that if we change them, it's going to be really expensive to go fix later. The vehicle will have a certain miles per gallon. Is that something we need to fix at the beginning? Probably not, right? What should be the miles per gallon for the vehicle? I should say kilometers per whatever. Do you use gallons? Whatever it is, whatever that ratio is. There's things that we don't have to fix early that we often do only because it's time to fix them, right? Okay, here's the time to set the requirements. Let's set them all. Why? Because it's time to do it. Well, could we delay that? Could we decide what the fuel economy is going to be later down? Sure, we could. Maybe set a range here. We're targeting 25 to 35 miles per gallon. That makes sense to me. I don't know what that translates into liters per whatever. But we can variable range here to say it's going to be in this range, and then eventually it's variable to start, but eventually it's going to become fixed, and surely by the time we're done, it completely becomes fixed. So that's a different mindset that we have to get our hardware and traditional engineers to think, that you don't specify everything up front. In fact, being flexible gives you added value and added economics later. How often have we got down later inside of a program and some poor engineers looking at, gosh, if that number were 13, I'd be done right now. But somebody specified it and said it was 15. Well, why'd they say 15? Because they had to put a number in the requirement document back here. Down here, they put 15 in because I just had to, right? And instead, what if I just said, well, sometime it's somewhere between 10 and 15 is probably going to be good enough. So keeping specifications variable can add gives a lot of flexibility to the developers and gives a lot of value and economic value later on. So anyway, we have the notion of fixed variable solution intent. That's where we're going to capture all this analysis and design stuff, requirements analysis, design stuff. It's in safe, but we're going to take a different mindset towards it. We're going to allow things to vary and evolve over time. Certainly by the end, everything's fixed, but we don't have to fix it up front. And then that's going to drive capabilities and features we have in our backlog, which is going to drive the roadmap, right? And the big difference between that is that in traditional engineering, we're going to have a fixed specification and a fixed schedule to go build it. Okay, and then everybody's goal then is just meet the schedule. We're successful if we meet the schedule. Agile doesn't want to just meet the schedule. Agile wants to do what? Every increment we want to do, deliver the what? The most value, right? Well, just because we're implementing a schedule doesn't mean we're delivering the most value. We want to do things in smaller batches, get feedback, learn, make adjustments to go continuously deliver the most value, right? And so that's why we do need to forecast for sure. But that's why we have a roadmap. The roadmaps replace those fixed schedules, and the roadmaps are variable. Okay, and the notion here is that instead of doing these things in large batches, we're doing them continuously. That's what the little icons are here to show, is that all the time, every increment, we're making small minor adjustments to the solution intent. We're grooming features and capabilities of the backlogs. We're making adjustments to the roadmap based on learning. Okay, and we're trying to contrast the fact that this is the way we did things with the waterfall approach, and this is what we're doing things from an incremental approach. Oh, there's my hundreds of statements. Okay, I did that. I missed that. All right. Another thing we like to do is decompose requirements. We have system requirements. We have those requirements down to subsystem people and say, hey, here's your system requirements. Now you tell what your subsystem requirements are going to be, and then your component requirements are going to be. Sometimes we need this level of detail for compliance reasons. Like the only certification body that I'm aware of that makes you do subsystem requirements is the FAA for flight certification. So in those cases, yeah, we do have to have system requirements and subsystem requirements, and we do the extent necessary we have to. And those, by the way, would be stored in the solution intent. We'd have those in there because we need them for compliance. But the minutia, do we have to detail what the screen's going to look like? Do I need a shall statement down here that says the screen is going to have a button for somebody to click, and it's going to be this size with this color? And eventually the level of detail is beyond the need we have to certify the system. And that's frankly why we have backlogs and roadmaps, right? So the details should be specified by the team members and the art members at the appropriate time. What we do so often is that we want to specify the system early with a fixed specification to a very detailed level, right? And then we hand that off and say, great, we've done all the thinking for you, just go build it. And the reality is these systems have so much uncertainty, so much unknown, so much innovation that they have to be changed. There's no way to change. There's no easy way to change those things. They're not designed for change. So we still have the notion of the specifications that we need to have, but put all the rest of those details in backlogs and roadmaps. Let the teams figure it out. Give them some autonomy and authority to go make those localized decisions. That's why we have product managers and product owners, that hierarchy that has that authority to make those decisions, define, build, test, deploy at the team level and the art level. All right, next thing we have to do is design for change. Something that we've known well in software architectures. In fact, back in the 90s, architecture was a big thing in software, the software community, and it has served us well. The fact that we talked about component-based architectures, which became microservices and everything communicated through a well-defined interface, that has served us very well in the organizations like the Spotifys and the Googles and the Facebooks that have taken that to an extreme. They have relatively independent teams that own specific microservices that they can then they own and manage and deploy those things and can own them. Excuse me, just 1 minute. Hey, dog stuff. At least he's not barking. So anyway, where was I? Design for change. Yeah, so the smaller the components we can have, that allows more independent development, independent autonomous development, all the way down to, we've done those microservice up teams. Individual teams can independently define, build, test, deploy, and launch and release their own unique changes, right? So this notion of designing for change is important. And the fundamentals here, we have modular designs, right? We have small components that communicate through well-defined interfaces. And so long as those interfaces remain relatively stable, then for example, in this example we have here, there's a camera in our autonomous driving car that's going to be, capturing imagery, and it's going to be sending that signal off to vehicle control. Vehicle control is going to interpret that imagery and make decisions about where to drive, where to turn, where to brake and accelerate and whatnot. Then that camera also has another interface that has to be mounted somewhere on the vehicle body. So it's going to, that's another mount point. And there's constraints there in terms of probably weight and vibration and I don't know, snow and clarity. Maybe I have to put it's actually true there. I talked with the GM folks, and for those cameras, they have to put defrosters in them and ways of cleaning those camera lenses, because if you're going to do autonomous driving, you can't block them with snow or mud or those other types of things. So anyway, there's constraints here. There's actually there's an interface there that you have to describe that interface, in terms of the characteristics of it. So the point here is that just like software, hardware has components. Software has interfaces between those components. Here's an electrical interface, example of electrical interface using a standard. And here's a physical interface that can be described with weight, vibration, could be heat transfer if it's a different kind of, so that connection point also has characteristics as well. Okay. What those interfaces do is they allow independent designs. So the fact that if I'm on the camera team here, my electronics group can independently evolve their designs, right? And I can give you new versions of I can integrate with my next version. I start out with a dev kit. I don't have any hardware yet. Well, I've got this dev kit that's got my FPGA, my field programmable gate array. It's an electronic component that allows it, it's a programmable device. And I can just use a dev kit, and I'm sending you an HDMI signal out here, and I'm writing some logic in there. Oops, while we're designing the first circuit board. We get that first rev of the circuit board. Maybe we're 3 or 4 months in, we got the first rev of the circuit board. Great, now I'm putting my logic on the circuit board. But from vehicle controls perspective, it's just an HDMI connector. I'm plugging in the next thing, right? And so I'm evolving my electrical design independently of all the other teams up here that are evolving their designs as well. And we can continuously integrate these changes as frequently as we want to, based on that. Likewise, in the mechanical side, right? There's a physical connector here. So I may have my virtual model, my CAD model, and we might integrate the CAD models, right? Digital engineering, kind of the beginnings of digital twins. We're trying to do some analysis, do we transfer heat properly or weight properly, or the holes work, the holes align, those types of things. So we can do the analysis work digitally, and then maybe we start 3D printing them. We actually go to a prototype world. We're actually going to print things. And eventually we go to the physical world, where we go to the manufactured product to make sure that things are going to fit and work before we go start a manufacturing process. But the point is that the vehicle body and vehicle control are also doing their own iterative designs. But because we have these interfaces, we can go check that the changes we're making in all the parts of the system as we integrate them continue to work well. And this really is what enables us that exploration of independent design sets, set-based design, right? So I can explore changes in my hardware stuff and changes in my 3D printing and all the dependencies here. Is this board going to fit inside that enclosure, and is it not? And all those questions are really encapsulated inside of here and don't affect anybody else that's working on the system. So how do we design for change with electrical components? So there's some things to be concerned about. If we're designing for electronics, it's interesting in the automotive industry. How many people have heard of ECUs, electronic control units, kind of in the paper, right? It's cars have hundreds of electronic control units. Well, those are really integrated circuits that are customized and manufactured with the logic hardcore built into them, right? So you have a braking system, and I put some logic in this braking system, little electronic component, stick it on the car. It can't change. It will never change. That logic, once it's burned into that electronic component, can't change. What happens when I want to do over-the-air updates, either in the operational environment or when I'm developing? If I'm a developer at say General Motors, I'm thinking General Motors. What's an Australian car company? You guys have? Is there an Australian car company? Here's an example.
Not anymore.
Not anymore.
Yeah, used to be Holden.
Oh yeah, okay, yeah. Well, I use General Motors as an example. So I'm an engineer at General Motors, and I want to make a change. I can't change the logic. The only way for me to change the logic in the braking system is to actually go manufacture a new part and replace it in the physical environment. So you see a lot of moves now away from ASIC devices into programmable devices, FPGAs, field around freight arrays, system on chips, or even CPUs, and most of the new car architectures that you see being built, they're favoring these programmable devices because the logic is now programmable, not just in the operational environment, but also in the development environment. We can learn faster in development engineering as we go make updates. I live in the Phoenix area, and Waymo, we're the big research area for Waymo, right? Waymo is Google's autonomous car company. And I tell the story all the time that I see Waymo. If you go stand in Chandler, Arizona, you can't stand for 3 minutes on a corner without seeing 5 Waymo cars. They're everywhere. In fact, it was really cool. The first time I saw a car with no driver, I had to walk up and take a picture of it. It was just amazing, right? This car is driving around, doesn't even have there's nobody in it. Well, how often do they change the software in that car? Is it every year? I mean, that's a long delay for learning. Is it every month, every week, every day, every hour? Certainly I would bet daily they can change if they choose to, right? Well, that means I'm not going to manufacture a new part every day. So anyway, the point is we're seeing a big shift from electronic components to things that are designed for change. And also about how we mount them, right? If we solder's cheap, it's easy, it's fast, but it doesn't allow for change. If I do have to replace a part, we want to use a connector, some kind of connector, which you guys are familiar with. Same thing with mechanical parts. Do we join things by welds or do we join things by some kind of fastener? Also, the software linkages that should be software controlled. This is one thing that Tesla does that's really cool. Almost every linkage in the car, mechanical linkage is software controllable. All the trunks, all the windows, all of the door locks, even the window, the little vents in your car. Anybody have a Tesla? I didn't know this. My girlfriend got a Model Y. If you want to adjust the vents, the air vents, you go to the screen and pinch out, and it's actually software controllable to control the little air ducts. Amazing. They future-proofed everything by saying if there's a mechanical linkage in the car, we're going to make it software controllable because we may want to change it later for some reason. Pretty cool future-proofing idea. All right. Last but not least, we want to frequently integrate the end-to-end solution. I hate to keep giving Elon Musk examples because he's becoming kind of a goofball, but we're going to give him anyway because he does have great examples, unfortunately. So most people are familiar with SpaceX, right? SpaceX started, I don't know, about what, 15 years ago or so, maybe almost 20 now, 18 years ago. But they have really taken over in space launch. And again, they were a company focused on learning. How can I learn how to launch rockets better? Right. And so there's a great quote here. This is Elon Musk with having an interview with the head of NASA. He was the director of NASA at the time, Jim Bridenstine. And they were talking about, what NASA's learned from SpaceX, right? And basically it's the willingness to fail, right? NASA has lacked that willingness to fail, but SpaceX wants to move fast. And if you move fast, there may be failure along the way. Not every launch is going to be successful. Right, but that's okay because we learned something from that fast launch, so we won't repeat it the next time, and be able to take that knowledge and reintegrate it. So really, it's this focus on learning how fast, and the analogy is I've worked on NASA programs, and you start a NASA program, they're not expecting a launch for 6 years. Okay, we're going to launch that thing in 5 or 6 years. SpaceX does a launch every 2 or 3 months. Crazy. Right? They just launch another one. They figured out how to buy down the cost of making a launch. And think about that. What would it be like, and this is especially to hardware engineers, what if you could put something in the operational environment in 2 to 3 months and get feedback on that thing? What value would that provide? What learning could you get? And then what would it take to make that happen? What would it take for us to go from the hardware environment we have today to getting something in an operational environment? It's not the launch that's going to go to the moon, but it's going to be the launch that does some kind of experiment and comes back with some kind of set of data or some kind of new knowledge that we've gained from it. Right? Great way to think about what we're trying to get done with Agile. And the reality is that the people in the hardware domains, they experiment, right? They don't just manufacture a part. They do CAD models, they do analysis on them. They do breadboarding. They wire things together in breadboards. They build prototypes and learn from things. They do equations and algorithms that describe, forces and heat transfer and those types of things. A lot of times those algorithms are built inside the CAD models. So they're learning for sure, right? But they're learning as individuals, right? Typical learning as individuals. The mechanical engineer, there's a mechanical engineer. The mechanical engineer, yeah, he's doing his CAD modeling and designing, and he's learning along the way. And then the electrical engineer, he's designing his little board along the way, and yeah. And then there's somebody else that's, this is the image sensor, right? So there's an image sensor, and then there's the FPGA person. FPGAs are really more software. That's very software centric. I can load new software on the FPGAs. That's code mainly. So they're probably agile people. They're just doing all their new code, and then they're waiting for the next rev of hardware so they can stick their code on that rev, and then I can stick my code on that rev, etc. But anyway, a lot of times this isn't done together, right? There's someone in another building, another part of the world that's doing the enclosure. Right, the enclosure is on a completely different team and person than the person doing the hardware boards. It's the different person writing the software code. But what we're trying to do is say we need to integrate that more frequently. let's take what you have, let's take what everybody has, and let's put it together and see what we've got. Right? It's like a pull event. So this is an incremental learning cycle, right? We want these cadence-based learning cycles where we're going to learn about what the system looks like as a whole. We're not going to wait to integrate 9 months, 12 months, 15 months. We're going to integrate frequently. In fact, the integration cycles in automotive are not 6 weeks. Every 6 weeks, right? I mentioned that I was working on that Sync Gen 3 program with Panasonic Automotive. We sent code and sometimes hardware to Ford every 6 weeks. Ford wanted to integrate every 6 weeks. This was a 6-week cadence. Why 6 weeks? Well, 12 weeks is too long to go. I gotta deliver another car in 18 months. If it's every 12 weeks, I get 3 learning cycles. If I cut it in half, I get 6 opportunities to make an adjustment versus 3. So the faster the cadence, the faster the learning, and the more frequently we can make adjustments. Right. So that's something we say, but there's kind of the tangible reason of why. Right. And I love Dontar's quote here that integration points control product development. We don't know what the product looks like until we integrate it. That's what the product really looks like. Beyond that, it's just speculation and injecture and those types of things. So then it's beyond just the camera team, right? That's the camera team integrating. Well, what about the end-to-end? Is there an environment that we can put it that's more operational? And most, as I mentioned, those cars driving around, Chandler, Arizona, the place where I live, or maybe on a test track. So there's ways to integrate these changes more frequently. We put them in a test track, put them in some kind of environment where we can go get richer feedback, deeper feedback across that big old collection of value streams, right? And then finally, I should have, what slide are we on? 30. So pretend that, oops. Yeah, this image right here, this is the vehicle supply chain. Yeah, so that's really what we're trying to show here. So here's all that, those value streams are all these guys right here. Right, so here's all the value streams. How do we integrate them end to end up in a vehicle program? So I'm providing powertrain, and I'm providing vehicle bodies and cameras. Well, those are up here on the trucks and the sports cars and the sedans, right? We have to integrate the whole supply chain as frequently as possible. And we do this as continuous as we can, right? We want to, as frequently as possible, integrate the end-to-end system. Every increment, we're not going to grab something from everybody, but we're going to grab something from as many people as we can. And then there's a roadmap. There's a roadmap that lays all these out. We have roadmaps here that lay out that are forecasting we're going to try to integrate. And there's aligned roadmaps down here that are saying, okay, here's how I'm going to contribute to all those roadmaps. And then as any one of these has a hiccup in it, well, the hiccup gets set up to here. We readjust these roadmaps, which then drive back down here to those roadmaps. As an example, with Panasonic Automotive, the Bluetooth chip was behind. It got behind by a month or two. So we had to take Bluetooth functionality and push it out, which means we had to pull other functionality and move it forward, right? So aligning our infotainment roadmap, right? Because the Bluetooth people up here got behind, that bubbled up to the top and then came back down to us to make sure that the whole supply chain is aligned with it. We get the most value out of every increment. All right. Last but not least, shift learning left. So really the goal of all of this is to try to learn faster, right? Learn faster than the competition. So again, back talking about NASA versus SpaceX, right? Traditional approach of NASA was we're going to launch in 6 years, and SpaceX says we're going to launch every 3 months. What that has done is SpaceX has now won almost all of NASA's business. So if you look here, here's all of NASA's launches down here. You can see they launch anywhere from, they do about 30 to 40-ish launches, every 2 to 3 years. So maybe about, 10 a year or so. Backing up a decade ago, SpaceX was getting about 5 of those a year, and other NASA contractors getting 23. Look at how that's evolved over 10 years. They get all the launches because they have figured out how to make launching more cost effective, right? They're reusable rockets. They manufacture rockets. How can you possibly, oops, let me back up a slide. Like, how can they launch? I can't read those numbers. This was a month apart. This was 3 months. This is another 1 month. This is another 1 month. How can they launch that fast? Well, they do things like they have the largest metal 3D printer in the world on site at the launch pad down in Texas. So when I have the next fuel, when I'm designing the next fuel tank or the next nozzle, I'm not going to manufacture that someplace and then ship it out by train and then assemble it over here. Instead, I'm just going to manufacture, I'm designing and manufacturing all in the same place. We talk about DevOps, right? The engineering work is going on at the same place we're doing the operational stuff, the operational environment. So we have DevOps we talk about in software. This is engineering and production going on in the exact same place. I engineer something, I get it in production right away, I get feedback so I can re-engineer, put it in production, re-engineer, put it in production. And they have made it possible that they can, it's the small developer changes aren't happening every minute or every 5 or 10 minutes like we talked about earlier in software, but the small developer changes are certainly happening every month or two. That's pretty good. That's better than every 5 years, right? Because they have gotten engineering and production and they've made their continuous delivery pipeline in hardware, right? We're learning in it, and we'll talk about that in a minute. So that's the investment that really SpaceX and Tesla and other folks have made, is we have invested in the CDP for software. We talked about how we didn't have Kubernetes, we didn't have all this automated testing built in and all the infrastructure that we have today. And we had to learn over 20 years in software how to build all that out. Well, we have to have empathy with our hardware people because they're back where software was 20 years ago, right? They're figuring out what their CDP is going to look like. They don't know haven't discovered their Kubernetes and automated test infrastructure yet. They haven't developed those. But I love what Elon quote here. He said the factory is the product. I'm not building SpaceX rockets. I'm building the machine that builds the SpaceX rockets. That's what I'm investing in. I want to be able to build rockets faster, so I have to build the machine that builds the machine, right? And I still get goosebumps hearing that because it's true. I mean, that's what we do. That's what we've done in software. We have, how much money did Google and Facebook and all those guys invest in all the infrastructure? And then they gave it to open source, right? Google built Kubernetes and gave it to the open source community and said, we don't want to own this. We're just going to leverage it with everybody else, right? They built that infrastructure out. And it's also a big change in mindset for hardware engineers, because hardware engineers are saying, give me a spec, I'll build you one product. That product is shipped and it's done, and I'm going to go build the next product. Well, I hate to give Elon credit, but he's really disrupted that, right? Why do you buy a Tesla? You buy a model year 2007 Tesla. It has the same value as the model 2012. It's got the same software because they can do over-the-air updates, right? That it's just like my phone. I expect that this phone, you can't see it's there. I expect that my phone will gain value over time because I can update my apps. I can update the OS. I can update things. But the only thing I can't update is my camera. The only reason I buy a phone nowadays is because I want a better camera. That's really the only reason, right? Because I can't, that's not modular, it's not replaceable. But even Tesla's designed things to be hardware replaceable. When they first shipped the Model Y with hardware 2 in it, they knew that the brain that was going to do autonomous driving was not the last one. But they still want to monetize the car, so they sold those cars. Yet they designed it so that was field replaceable. You could pull out the board that was going to do the logic for autonomous driving, because they were using the NVIDIA chip at the time. They were going to design their own chip. This is like 4 or 5 years ago. So you still design those things to be replaceable operationally. All right, I'll wind this up. So really for hardware, we want to explain that learning occurs in 3 environments. There's the virtual world, right? We're doing analysis and design. This is where we do digital engineering. We're trying to connect those CAD models one to another, right? So we can go do fast feedback, fast learning, small changes. Eventually, we've got to go into some kind of prototype environment. We can do 3D printing. We can do mock-ups. I see organizations do wood mock-ups where we print before we actually go manufacture metal. We're going to do wood mock-ups to see if things work out together. That missile company I mentioned, after their very first PI, they had 3D printed some parts, and they had learned something that would have cost them a bunch of time if they had waited 3 or 4 PIs before they actually discovered that. So the 3D printing, I remember them talking about that by prototyping things, they can learn fast. And eventually, of course, we're in the operational environment, and all those give feedback back to the engineering work we're doing here. So we want to use those virtual environments we use the physical environments to validate the virtual ones. This is where we do our hardware. Hardware engineering is done in the virtual environment. It's all done in CAD, right? We do mechanical CAD, electrical CAD, chemicals, all that stuff's done in engineering type environments. But with digital twins, right, we want to have the prototype environment and the operation one validate that virtual environment. In fact, I was in Europe about 2 or 3 months ago, and I talked to a Volocopter, and they certified their digital models. They're for flight certification. They don't have to recertify the actual helicopter. They recertify their digital models because their digital models are so accurate. Just kind of the same thing Joe Justice mentions here, that I can make changes in my car, certify the digital model, and then push those changes out to the operational environment. All right, last but not least, last slide. Learning requires psychological safety. If the very first time the rocket blew up, if Elon Musk had gone to the team and said, you can never blow up another rocket again, what would that have done to the culture for learning, to a continuous learning culture? It would have stifled it, right? Instead, you've got a guy like the CEO of the company. The minute one of these misses looks like a failure, right? It has a spectacular conclusion, makes the news, SpaceX rocket blew up. What does the CEO say the next day or the next minute? Hey, here were the problems, but we got all the data we needed. It was a successful mission because it was an experiment, and we learned, we gained knowledge, we gained new knowledge, we learned from that experiment, right? Hell yeah, great job, team. Boom. So with that, I'll end it. So hopefully that gives you some kind of sense of how we're explaining Lean Agile practices and direction and product development to the hardware engineers. We don't have a lot to tell them yet in terms of, in software, we could tell them, hey, here's the best practices for your environment, your dev environment, developing these languages, use this tech stack, right? We have that knowledge now, right? And vendors provide it. We don't really have that tech stack yet. We're still helping them figure that out, I would say. But the principles still apply, right? And we'll get there. And the winners will emerge, right? That's why going back to this slide, I think is kind of important. Oops. The winners have yet to emerge here, certainly in the hardware space, right? So those that learn the fastest and figure this out will be the ones that, are the victors. I think that in the automotive industry, there's a bunch of brands. There'll be consolidation. There are new brands entering the market that will survive, and there are legacy ones that may not survive that we know because there's big disruption going on. So, now's the time. And that's why I think we're getting a lot of pull from certain domains and certain organizations. Were there any questions in the chat? Nobody raised their hand. I was actually watching. Nobody raised their hand. Well, except when I asked you to raise your hand.
We had a question that was from Sandeep. He was really trying to ask for some questions or some tips from you, Harry, about a mindset change for hardware folks. It's obviously it can be a really big shift for hardware folks.
Yep.
Any thoughts there?
And that's, I think it starts with why. Anytime we want somebody to change, we start with, well, why do you want to change? And I certainly have talked to organizations, and I've spent a lot of time in automotive, and I think a lot of automotive people know why there's big disruption. If we don't innovate and learn fast on our competition, then we may not be here. I've also talked to automotive organizations who said, well, we really don't, we don't think we need to change. People buy our cars because they're very luxury brands. We almost build custom cars for people. People want to drive a car. They don't want autonomous driving. People don't want electric cars. They like to hear the engine go vroom, vroom, vroom. And that may be true, right? But if there's not a lot of opportunity, if they don't see a need to change, then it's hard to start with why. But usually for me, we know the mindset change. We want you to Lean Agile mindset, Lean Agile principles, right? And then adjust your practices to support those Lean Agile principles. But also before you change your mindset, you have to want to change your mindset, which starts with why, right? What's the reason you want to change? I would say. And then Rob's got a question.
Yeah, thanks, Harry. My question was just in, I suppose, the organization of that sort of supply chain from those different disciplines. And when you think about the construct of your agile release trains, your solution trains, especially when you're supporting multiple products, you've got common hardware, you've got common software, but you're adjusting and tailoring to different industries or different applications. I'm interested in understanding, I suppose, some examples of how that has been structured well, and if there's any sort of potential gotchas that can be avoided, or and maybe it's a broader topic that might need more time, but it's something that I would really appreciate some guidance on at some stage.
Yeah, so let me take a stab at it. So, if we pick on any one of these, like powertrains probably got 1,200 people on it, braking systems will have 800 or 900 on it. And they will not just produce one powertrain solution. They will, economies of scale, right? They will produce a product line of powertrains, a series of solutions, and they'll have some common components, and they'll have some common infrastructure in here to make that work. Right, so I'm a value stream that's delivering not just one solution, but a product line of solutions that could be integrated up here. That's different, frankly, than if we put powertrain in every one. In fact, I've worked in aerospace as well. And if you go look at aerospace companies like Honeywell, which I've worked at before, they'll get a request for a flight control system, and they'll be from Airbus, and they'll start working on a flight control system. They'll get another request for a flight control system from Boeing. Well, they'll just branch some of the Airbus stuff into the Boeing stuff, right? And they'll copy all the errors with it, and they'll copy all the, so you end up having to fix defects multiple times because you got multiple code bases that kind of started from each other. And they're not getting economies of scale, right? They don't have a product thinking, they have a contractor thinking. And instead, when we were talking to them, this is a few years back, instead, you should be thinking in terms of, we have a product that's flight controls, and that product has a series of product lines that has variations, and we've got a roadmap on the features we're trying to build into our flight control product, and we will try to match our roadmap with customers as best we can, but it's a mental shift, right? That's a different mental model of, instead of being a contractor that says, I'll just listen to every one of your whims. I mean, it really depends on the industry too. The avionics industry, it was all about how fast can we get to market with these new planes. They didn't care as much about cost. So they're willing to pay the overhead to do a bunch of one-offs, right? One-off flight control system for this, one-off flight control system for that. Then they became more cost conscious, so if I'm more cost conscious, I've got to be thinking more, instead of embedding powertrain everywhere, I'm going to pull powertrain out of all these places and put it in one spot and have them provide a solution, a series of powertrain solutions to those folks, right? So different mindset and how we organize. Did that address the question to some degree?
Yeah, thanks, Harry. That's good.
Yeah, sure. I'll mispronounce this as Puneet.
Yes, Harry. Can you hear me?
Yeah. Yep.
Yeah. First of all, thanks a lot for presenting such a nice content. I'm very happy to see how agile or safe is applicable in manufacturing industry. At the same time, I was wondering, like, safe have accommodated lots of good and best practices in the market. How about the Six Sigma in order to build our product and design better and better? Do we have any plan, or because one of my client in Sweden, he is asking, like, how Six Sigma and Agile can mingle together, and I'm working on the papers for that.
Well, so Six Sigma is really about quality, right? How do we,
So Six Sigma, there are, like, 2-3 aspects of Six Sigma. One is, like, defects elimination and error-free manufacturing. Yeah. And the other aspect is, like, quick problem solving. It's a data-driven problem solving. So where we call Y is equal to FX. So that is one aspect where, like, Six Sigma can complement all the safe initiative, because Lean is already accommodated, right? So Six Sigma is the only one which is missing at the moment.
So I don't know that. So we incorporate Lean because Lean is principle based, right? So we think we incorporate Lean principles pretty well, and organizing and flow and those types of things.
Absolutely
Six
agree.
Sigma,
VSM,
and I'm not
VSM,
a like a
5S. Yep.
yeah. Six Sigma wants to do quality, right? And be so I don't think we are against any of those practices for total quality management or Six Sigma, those quality. You know, we talk about building in quality. In fact, the next version of SAFe, we're going to have a much beefier built-in quality discussion. You know, so we talk about building quality and we need to build quality in. Are we specifically borrowing from Six Sigma or total quality management, TQM, or any of those other practices? Not necessarily, but I think those drive a bunch of the practices that we see today, right? They were first, right? They were early on in focusing on quality is everybody's job, that type of thing. So I don't know that we have them specifically built in, but that doesn't stop someone from adding them as part of their quality practices. I will say this though, that manufacturing a lot of times, to me, over rotates around trying to lean out a process. Failure is okay if it can be controlled. I love Don Reinerson at one of our summits talked about, you know, the fact that variability is good, right? Variability when it's controlled is a great thing because it lets us experiment and learn and get feedback and make adjustments, right? So we don't want to be too lean and we don't want to be too Six Sigma because we want to have failures. We just want to constrain them. You know, he gave the great example of if I'm going to deploy a change and it's going to hit everybody, then the cost of that change is dramatic if it fails. But instead, if I deploy a change and it only hits 10 people, well, I'm constraining the collateral damage, constraining the damage of that change. So it allows me to deliver more frequently. I don't have to test more. I can reduce the cost of my tests. I can reduce the cost of my deployment, and I can deploy more frequently because I've constrained the scope of the potential damage. Right. So when I think about those legacy things, I don't think they have an agile mindset in terms of trying to constrain the scope of the damage and then being able to learn fast. Right. They try to too much focus on trying to reduce waste and reduce that cost. So I'll just caution that. That's one thing where I think I thought in the past where we have conflicted to some degree.
Yep. That makes sense. But I mean, like as a Six Sigma the professional, I feel that when you are talking about the cost of delay, cost of quality, then cost of quality is one of the concern which is huge. And also the other aspect is problem solving. So in SAFe, we have discussed about the problem solving fishbone and Pareto principles. Yeah, but they are incomplete without FX. Y is equal to FX, where we calculate the number of X factors and then individual magnitude and weightage.
Right.
And it's a data-driven framework. And that's a big aspect of Six Sigma. And I'm very excited to see all these aviation industry example you have given. And that, like, you know, makes me very comfortable and confident, like, yes, I mean, this SAFe is applicable not only in software development, but also, like, you know, at a huge prospect, especially the aviation industry. And aviation industry is incomplete without Six Sigma. You know, where the margin of error is very small, you know, and the losses are quite big. So yeah, just think about it. I mean, like, it's just a suggestion. I mean, yeah.
Great.
So thanks a lot once again. It was very nice contents, and it makes me very excited. Thank you.
Great. Yeah, thank you. Thanks for the comments.
Yeah.
All right. I think if I look at the time box, we're about 10 past the hour, and I'm sure we could ask Harry questions for hours and hours and hours, and I sure could. And Harry has been you've been really generous with your time. So I'm gonna just bring us to a close here, team, and thank Harry very, very much for your time today and your thought leadership and sharing the insights of where Scaled Agile has gone and some of the guidance that Scaled Agile is providing to the industry with regards to hardware engineering.
Well, great. Thanks everybody thanks for attending and thanks for having me.
Yeah, thank you. I will be posting this chat on our website in due course, and we'll share that out with folks. Thanks everyone for attending today. Thanks again